All right, this is a lesson on what is called integration by use substitution. It's actually a way to give us a way to integrate a problem that has a chain rule in it, in essence. So we've had some pretty simple antiderivatives. For instance, we had this problem last chapter. The integral of sine x we just know is negative cosine x plus c. No problems, straightforward, what I call those one-step antiderivatives. However, if you get a chain rule in a problem, things got a little trickier for you last chapter. Like you had to find a way to deal with this. You said, hey, well, I know that there's got to be a negative cosine 5x in this answer, but if I take this derivative, the derivative of this is going to be sine 5x times 5, which means my answer had to be divided by 5 to make it work out. So what use substitution is going to do is going to allow us a way to not have to think this through. We're going to be able to do what's called a substitution, and that's going to work itself out for us. And if you look at this first problem, this problem would actually be easier if that 5 was there in the first place. That's a little clue in for what's going to happen. Notice that that 5 happens to be the derivative of what's inside part of the composite function, which actually helps us. So let me do a little racing here. Use substitution can actually be proven. There's a little proof in the book. It's right here, actually. I'm going to send this to you. I don't think the proof's that important, to be honest with you. It's just about learning how to do the method. So just to show you that same nice, simple little example, if we have sine 5x dx, what we do is this. We're going to pick a part of the function and just call it u. Typically, but not always, and this is where it gets a little tricky. You have to do a little guess and check. Typically, you make the u your inside part of the composite function. So notice there's an inside part of the composite function. So I make my u equal to 5x. If my u is equal to 5x, if I take the derivative of this, that means du equals 5 times dx. Derivative of 5x is 5, kind of like differentials. Also means that if I solve this piece of the little equation here, that dx is equal to 5 over, is equal to du of 5. I can now go back and do what's called the u substitution piece of it. I go back into my equation, I go sine that 5x is what I decided to call u. But notice that dx is du over 5. And that 5 is just a constant, so it can go anywhere. So if I rewrite this as 1/5 times sine u du, notice that I now have a new integral with new variable in it, and it's u. Now I can just integrate this with respect to u. So 1/5, this is going to be a cosine u negative plus c. And then notice that u, I just have to go back to that u, which is 5x. Same answer I got the other way without the trial and error piece of it. Very simple problem, very simple explanation, but just to kind of get you started. The problems are going to be more complicated than this. So, basically what I have here, and these are in the notes also, and I'll do a couple of them right now, there's a whole bunch of just examples. So, I'm going to show you something that might make it interesting for you, is that if I have a composite function, even something, we had a problem like similar to this on the last test where you had to multiply that out. Power rule doesn't work. Notice if I were to try a power rule and do x squared plus 9 to the cubed over 3, if I check this with my derivative, drop that power, I get x squared plus 9 squared, which is right, but then I also get times 2x. So this problem would actually be easier. Notice that doesn't work, but if that x was in this problem in the first place, it would actually be an even easier problem to do. So what you look for here is this is now my new problem. So I'm going to just rewrite it so you can see it better. if I gave you this problem last chapter, your only option would have been to multiply this out and multiply it through by x or just do power rules. Kind of a pain. But now you can do u substitution, because notice, if you make u equal to x squared plus 9, which is the inside part, notice it's the inside part of the composite function. Typically in a u substitution, what you will make you have to decide what to make u, you have to do a little guessing and checking, but typically you make u equal to the inside part of the composite function. So now notice that du equals 2x times dx, take the derivative of that, and then dx equals du over 2x. Now when I go back and substitute, that x is still there. This x squared plus 9 is my u squared, but my dx is du over 2x. Notice the nice thing about that is because that x was there, it cancels, and now I get 1/2 times the integral of u squared du. My integration is now all in terms of u, so I can integrate that. I get u cubed over 3, which is u cubed over 6, but u is this. So the final answer is x squared plus 9 cubed over 6. Notice what made that problem work was the fact that the inside part of the composite function's derivative was there also. So I'll erase that one. Maybe I'll just give you kind of one more example. When you do these problems, it's just a lot of guess and checking, really. So I have one, and I'll just put some limits on this one too, because sometimes you're going to have limits, sometimes they're not. Doesn't really work any different. I got another example, that's tangent x, secant squared x dx. This one's a little trickier because there is a composite function, but it looks a little bit different. So again, sometimes you're just going to have to guess. And one thing you want to look for is, thing number 1 is look for composite function. Thing number 2 is look for the derivative of something that's already there. So notice the derivative of tangent is secant squared. So that's actually an advantage to us. We could try to simplify this, and it might simplify nicely, it might not. But if I just make u equal to tangent, because that's secant squared is the derivative, now my du is secant squared x dx, which means my dx is du over secant squared x. So when I substitute, I got 0 to pi over 3. My tangent is my u. I still have that secant squared x, but my dx is du over secant squared x. So those will cancel out. And I'll be left with u du. And now I have u as a variable, so I get u squared over 2, but my u is tangent x. So tangent x squared over 2, and now we're going to integrate from 0 to pi over 3. I'm going to skip that step because I think you're capable of doing that, but that's kind of the basic idea. So I'll do one more real quick. There are other examples in the book that might help you. It's really, at first, just kind of guessing, trying things. You just got to take a guess. Again, sometimes you'll have a nice, easy, obvious one where there's a composite function. If there's a composite function, 99% of the time, if you make u the inside part of the composite function, it will work just fine. But notice no composite function here. But notice a function, x squared minus 4, and the derivative of x squared minus 4 is 2x. So its derivative is sitting there. So if you make u equal to that function, your du becomes 2x dx, and then your dx becomes du over 2x. Things are going to cancel out nicely now. We go back in. That x is still there. The dx is du over 2x. And then the x squared minus 4 is your u. Cancel. And you get 1/2. That's just a constant. I'm going to pull it out. And I'm going to write it like this so you can see it better. Notice what's going to happen. I mentioned this last week. A lot of times after you do the u sub, you do all this work at the end. You're going to get lots of things that look like what was on last chapter's test. Power rules, one-step antiderivatives, that sort of thing. So that's why last chapter's things are so important. What over u is natural log of u, but u is x squared minus 4. And of course, I can tack on that plus c there at the end, and that's another example. So there are more examples in the book. I want to take a look at those. I know they might be hard the first time. Just guess things. Pick things for you. Sometimes you'll pick things for you and they don't work. You know what? Then you try something else for you. So the first few times doing these can be a little tricky. Some are very simple. But give these a shot. I'll be back in class on the block day and we'll go over that.